Differential equations serve as a way of developing complex equations that give a quantity from the value of another based on their relationship, starting from a simpler base relating the change of one quantity per the change in the other.
In electrical engineering, differential equations can be useful for deriving equations for circuit analysis. An RL circuit in electronics is one which contains only an inductor, a resistor, and a power source as components. The nature of an inductor means that the voltage used by it and a resistor varies with time. Firstly, inductance is defined by the rate of change of magnetic flux per amount of change of current flowing through it, while the voltage is equal to the rate of change of magnetic flux per time. This is known as Faraday's law of induction.
Equating the two gives the voltage through an inductor, V equals L by di on dt. Voltage equals the inductance by the rate of current change per time. For a series circuit, the sum of voltage drops equals the supplied voltage. So given Ohm's law, V equals IR, an equation for the voltage in an RL circuit can be developed. E equals di on dt by L plus R by I, where E is the supplied voltage, a constant, R is a constant relating to the total resistance in the circuit, L is the total inductance of the circuit, I is the current at time t, and di on dt is the rate of change of current in the circuit. Now we have an equation to solve.
The first step is rearranging the equation to set up for integration, obtaining the following. From this, we can integrate each side with the left-hand side respect to current at time t and the right-hand side respect to time. Taking the exponential of each side and rearranging e to the right-hand side, we achieve the following equation. From this, a simple division of r on each side occurs and simplification of the equation with background knowledge that at time equals 0, current equals 0, and therefore A equals E. This produces a conclusive equation for current through a circuit. Differentiating this developed equation with respect to time can further develop an equation to calculate voltage at time t. Recalling that voltage equals total inductance multiplied by the rate of change of the current through the circuit, differentiating both sides with respect to time, we obtain the following equation to calculate voltage in the circuit.
But wait, this equation could also be derived using the following method, as shown. Taking the coefficient of IT as PT and the constant as QT, we find an integrating factor RT. We can determine at t equals 0, I equals 0, therefore C equals minus E on R, which is the same equation for current as when the other method was used.
These equations are important as they help describe the behavior of inductors in an RL circuit, enabling their successful usage in present-day appliances. Inductors are primarily used in analog circuits and signal processing, a mandatory aspect in radios, for example. From these final equations, the current or voltage in a circuit at any indicated time can quickly be calculated and enhance circuit analysis for its given application. For example, calculating the inductor current and voltage when a switch is moved to another position, or calculating the inductor's total current stored at a given time in the circuit.
Thank you for watching our video. Leave a like and subscribe to join the resistance.